Okay guys, so in this video we're going to talk about the area of a surface of revolution. So first of all, let's think about some basics of like what is the area of a surface of revolution on some simple shapes, and then we're going to extend that out to more complex curves. So we're going to start with a cylinder. So essentially, if you think about if we have the volume of circular sectors, okay, we essentially create rectangles, which we then take a line and revolve it around an x. Okay, what does that mean? So if you recall, we kind of, if we had some curve, we would draw some line that we were trying to find the volume of. We would draw some line here, and then we'd rotate it, and we'd get some like cylinder, but it would be an empty cylinder. And we would create this empty cylinder with a surface area. That's what it was. And then we took the next surface area and the next one, and really, if you think about it, that surface area of a cylinder is just the height of that line. Okay, this height here, and this is the circumference. So the area it's a rectangle, so it's height times circumference in this case. Okay, and so basically, if we then integrate over the height and multiply it by the circumference, then we're going to be able to kind of get this surface area. That's what we're doing here. So whatever this height is, or if we turn it sideways, it would be kind of the length. So if we were instead thinking about our cone this way, it's like we would integrate along this, the height, and then we would do the circumference. And the circumference would obviously be 2 pi r. So r, whatever our radius is here. Okay. So we're going to extend that out now to more complicated shapes. So essentially, if we're talking about surface area of a curve revolved here, so we have some curve and we're revolving it. We're creating this shape. And if you think about it, this is our curve here, y equals f of x. This right here, this is the height. Now, this height you could call the y, or f of x, whatever you want to call it, but it's the y height at any given point. And so it is then being rotated, okay, as far as like the circumference of this rotation at this point would be the height at that point, y or f of x, and it would be times 2 pi to make it this 2 pi r, the circumference formula. And so we're essentially taking our 2 pi y, or f of x, and we're dragging it along this curve. This is the integral of the curve, the arc length, basically. If you recall, this is the arc length, 1 plus f prime x squared. That's arc length. So what we're doing is we're taking circumference times arc length. And a big thing that you need to keep in mind essentially is that what we call f of x, or whether we want to call it y, is kind of going to depend on what we're integrating with respect to. So in this case, if we were integrating with respect to y, then we would have a dy. And rather than call it f of x, we'd probably just call it y. And then we'd want to derive this thing, the derivative with respect to y, so that we get a function in terms of y as well, so it's all y's. If we have dx, then obviously we want to describe this thing here as something in terms of x. So if that means our y height, well, we call it f of x. So, and then we derive this thing again with respect to x because we'd want some x's at the end. So it's just a matter of this can be like y's, this could be dy's, and this could be maybe f prime of y as needed. Okay, so essentially, that's one of the ways that we actually think about this in terms of like Leibniz notation. Another way to think about it is that the surface area here is going to be the integral from a to b of 2 pi y times the square root 1 plus dy dx squared dx. So then this y again, it's probably not going to be left in terms of y since we're doing dx, so we'd probably want to write y in terms of x, but we get the idea there, hopefully. But we can also describe this if we instead called like x g of y, some function of y, where y is between c and d. Then this formula becomes the surface area from c to d. Again, c to d just because we want to make it different because it's along the y-axis instead of the x-axis. So we're doing it along the y-axis here, 2 pi y. So again, it's still y here. So essentially this is still rotating around our x-axis here, square root 1 plus dx dy. Notice deriving x with respect to y squared dy. Okay, so again, depending on how we need to do this, and so essentially the big thing to keep in mind is that this thing right here, whatever this is the radius of our object. That's kind of the biggest thing we need to think about. Beyond that, the radius needs to be in the unit that we're dealing with here. So in this case, this y here, we called this f of x earlier. In this case, if we're doing with respect to dy, if our radius is y, then we just leave it as y. No need to turn it into some function of x or whatever. Okay. So essentially, another way to think about this is both formulas can be summarized symbolically as the surface area is equal to the integral 2 pi y ds, where ds is the arc length. For rotation around the x-axis, so basically for rotation around the x-axis, we do it like this, and with rotation along the y-axis, about the y-axis, we would describe it as surface area is equal to the integral 2 pi x ds. And again, it's just depending on what our bounds of integration are. If we are integrating along the y-axis, then we want to make sure that we have this in terms of y. If we're integrating with respect to x along the x-axis, everything needs to be in terms of x. And so we use this formula for rotation around the x-axis and this formula y-axis. Okay. So again, to make this clearer, y-axis, and this x-axis rotation. And again, we use whatever we need. If our bounds of integration are in terms of x, integrate with respect to x on this thing. So that means that this y would have to be turned into an f of x, and this one would be using this one. If instead we were going along the x-axis, but we had a bounds of integration along y interval, then this would stay as y, and this thing we would then use this one. Okay, now you're going to see this in action. We're going to do this. All right. So, but again, let's take a look at that same concept now in a picture. So basically, if we look here, the circumference is 2 pi y, and then we have the arc length ds here. Okay. And in this case, if we're rotating around the y-axis, it's 2 pi x ds, where again ds is arc length, depending on how we want to describe that arc length. So it all just kind of depends how we want to describe the arc length. And again, if we describe the arc length in terms of y's, then this x would need to be replaced as like a function of y, gy. All right, so let's see that in action with a couple examples. All right, so find the area of the surface obtained by rotating the curve about the x-axis. All right, so let's start with a picture of it because I think that just really helps me cement what I'm dealing with. Y equals x cubed. Okay, and we're rotating about the x-axis from 0 to 2. So let's call this actually f of x instead of y. That way we can write it as a over an interval. So 0 less than or equal to x less than or equal to 2. All right, so we're dealing with this thing here, and we are integrating it along the x-axis because we have that, so we at least know that much. This is going to be the integral from 0 to 2, and we know we're then going to say dx. That's what we want to do here. Okay, so along the x-axis, again, if we're talking x-axis, okay, we're going to go to this thing. The surface area is equal to the integral of 2 pi y, because we're rotating this around, so this is the height here. Let me go ahead and snip it so I can draw on this image as well. Okay. So let me shrink this down just a tad. Okay. So again, we're using this one right here. The surface area is equal to the integral of 2 pi y ds, where ds is either going to be in terms of x's or y's, and since we're integrating along x, we're going to want to write it in terms of x. Okay. So let's go back to this and actually walk through that. So this is going to be, again, if we take a look at this picture here, if we were rotating this thing, we'd have some shape with a rotation where the r here would be the height, y. So right here, this is y, which is f of x. However we want to think about it. Okay, this is y. So essentially, our circumference would be 2 pi y, or 2 pi f of x, however we want to think about it. That's what we're integrating. And since we're integrating from 0 to 2 on the x-axis, then we want to write it in terms of x. And then we're going to take the square root of 1 plus our derivative with respect to x, because we want x's here. So that would be dy dx squared, something like that. So that's what we're going to do. So again, going back to what we're going to plug this in now, 0 to 2 pi. Now again, the radius is y, or f of x, our y, or f of x, but we want it in terms of x cubed, times the square root of 1 plus. Now we want to take the derivative of y with respect to x because we want it in terms of x. So that is, again, y equals x cubed. So y prime is going to be 3x squared. So that would be in terms of x. So we're going to use that one. So that would be 3x squared. And again, it is our with respect to dx, because we're integrating along the x-axis from 0 to 2. Okay. Now, if you think about it, technically speaking, right here, if we instead had said like, oh, where y is between 0 and 8, then we would have done a dy with the same basic problem, because it's still rotation is still happening, and we'll take a look at that in just a sec. So we have this integral. We're going to do a little bit of cleanup work. We have the integral from 0 to 2 of 2 pi x cubed. I know we can draw this out, but I don't really bother sometimes. 1 plus 9x to the 4th dx. Okay, now we have some great news with this thing. Surface areas can sometimes be actually really nice integrals compared to our the arc length, because with arc length it's just a square root, which usually sucks. But if we have a function outside, sometimes that function can be really nice. In this case, notice this is x to the 4th, this is x cubed. This can be u sub. So if we call like 9x to the 4th our u, then 9 times 4 would be 36x to the 3rd dx would be our du. And now all we have to do is create we have an x cubed here. We have a dx. We just need a 36. Well, we have a 2. So what we'd need is an 18. And so that would be a 1/18th outside. Okay, so while I'm doing that, I'm pulling this pi out since I don't really need it anymore. Pi 18ths integral from 0 to 2, but the problem is we've changed it. We're changing it into u, so it's no longer true. We can always change this bound of integration from 0 to 2 into our u form if we want, which we can do. I mean, why not? So if we think about that, if 9x to the 4th equals u, then 9 times 0 to the 4th is u. So that means this would be from 0 still. And then 9 times 2 to the 4th would be our u here. So 2 to the 4th is going to be 2 times 2 is 4, times 2 is 8, times 2 is 16. So 16 times 9, which is a pretty big number. I don't know what that is off the top of my head. 144. So we're integrating this 144 from 0 to 144 if we want to do it in terms of u. So du replaces our dx, our x cubed, and our 36. And so all we have then left is the square root of 1 plus u du. Now, if we integrate this thing, we can deal with this because even though this is to the power 1 plus u, this is to the 1/2, and this is linear inside, so this could be done with another u sub if you need, but we can also see it's just linear, so, and it's just a 1u anyway, so I don't really need u sub for that. But technically it is done through u sub. Okay, so power rule, raise it to the power by 1, so it's 1 plus u to the 3/2, and then we divide it by the new power, 3/2, and also by the derivative of the inside, but the derivative of the inside here is just 1, so it's not necessary. So I don't need that integral. So this is going to be pi over 18 times this thing from 144 to 0. All right, I'm going to clean this up a little bit. And again, because we changed our bounds of integration, we don't have to convert back from u into our x's. And like I said, sometimes I do that, sometimes I don't. It just depends on the problem. All right. So divided by 3/2 is like saying times 2/3. So we have 2/3 times pi over 18 times 1 plus u to the 3 over 2 from 144 to 0. Okay, so if we simplify this, this thing here becomes 9, this becomes 1. So we get pi over 27 times 1 plus u to the 3/2 from 144 to 0. Now we'll go ahead and plug these in. 144 in here, we get pi over 27 times 145 to the 3/2 minus pi over 27 times 1 plus 0, so it's 1, something like that. Okay, so cleaning this up a little bit, 145 cubed square root, that's like saying, so we have pi over 27 times the square root of 145 cubed minus pi over 27. So if we think about this instead as 145 squared times 145, that's what 145 cubed is. This squared can come out, and so we get 145 pi over 27 square roots 145 minus pi over 27. And that maybe doesn't look all that much better, but if we factor out a pi over 27, we would get 145 times the square root 145 minus 1. And this might be a little bit better. All right. Now, we can double check that this is, in fact, our area by checking our integral. I mean, double checking our integral, at least making sure that we did our integration correctly. So let's go ahead and take a look at this thing. Pi over 27 times 145 square roots 145 minus 1, since there's a lot of room for error here, right, in our integration. So I just want to double check. This is 203. Let's go back to our original integral that we did. The integral from 0 to 2 of 2 pi x cubed square root 1 plus 9x to the 4th dx 20304. All right, so as long as we set it up correctly, we at least did our integration correctly. So that's always a good sign. Okay, so I mentioned earlier that we could also have done this in terms of like from 0 to 8 instead, potentially. So let's take a look at that. All right, so again, in this case right here, we said from 0 to 2, but y could also have been from 0 to 8. That's what this point was, to 8. Okay, so realistically speaking, we could also have done this with respect to our y's here. So essentially, our radius here in rotation is still y, because we're still doing it. We're still rotating around the x-axis. Now, our circumference, this would be the integral from 0 to 8 of 2 pi y, because that's the the radius here, 2 pi y, square root 1 plus, now we want to integrate this thing in terms of y now. So we need to have a dx dy. That's what we want. And then we would integrate this along y. So if we plug in our what we find our dx dy, we can do this a couple ways. We could just treat it like an implicit if we derive this thing with respect to our y here. So if I say d dy of this thing, then what we end up with is 1 equals 3x squared times dx dy. And so solving for dx dy, again, this is implicit integration. we didn't need to. We could have solved for x as well by taking the cube root, but I just wanted to point this out. Divide by 3x squared, we get 1 over 3x squared is equal to our dx dy. Okay. So we can then plug this, oh, I didn't write squared here. Okay, so we can now plug this thing in, replacing our dx dy with what we have, which is 1 over 3x squared. All right, so now, but in this form we actually want it, sorry, when we did this thing, we found dx dy. We actually found this thing in terms of x. That's a problem. We don't actually want it in terms of x. So let's go back and talk about it in terms of kind of like a y here. Okay, so we have, let's think about this instead. If we wrote this as like x equals the cube root of y, then dx dy. All right, this is better. So that's how I knew I did dx dy in terms of not solving for it. So essentially doing implicit, which is possible, but the problem is that then that would give us it in terms of x, which isn't really what we want. So we want it dx dy in terms of y, and this is how we can manipulate and force it into the formulas we want it to be. Like, do we want it in terms of x or do we want it in terms of y? It just depends on our bounds of integration. So that would be 1/3 y to the, so this is like saying y to the 1/3, so y to the negative 2/3. Okay, so that is 1/3 y to the negative 2/3. And I'm just going to plug this in really quick and make sure that we get the same value, because I don't really want to waste time with this integral necessarily. I just want to show you that we can do this if we had set it up in that form. So the integral from 0 to 8 of 2 pi y square root 1 plus 1/3 y to the negative 2/3 squared dy. And if you notice, we get the exact same value we've already gotten. So again, if we had instead wanted to do it in terms of y, so if it's maybe easier to integrate in terms of y, then it might be worth doing that. But it really just depends. To be honest, this integral is probably worse, since this would be a like a cube root y squared, and that's not a very good form to try and do some kind of u sub, so that would actually end up being worse. But I just want to point out is that if we get an integral that maybe we don't like, then we need to try converting it into the other variable to try and make our lives better. All right, so it's really about our setup here. Let's take a look at another one. Find the area of the surface obtained by rotating the curve about the y-axis. Okay, so let's first start by graphing it. We have this thing. And notice we have bounds of integration in terms of x. So we're probably going to derive this or integrate this with respect to x, unless for some reason it's hard to integrate. Okay, so we have this thing. This is our y equals f of x here. So I'm going to call it f of x so that I can then shrink down this bounds of integration. 0, or the domain. 0 is less than or equal to x, which is less than or equal to 12 of this thing. So we're dealing with this. And like I said, if we're talking about it in terms of x, it's from 0 to 12. If we're talking about it in terms of y, it would be from 0 to this 13.856 approximately, whatever that is. It's 1/3 times 12 to the 3/2. That's what that is. But anyway. But obviously that's kind of an ugly number. So we're probably going to stick with x's here. So we're going to take this integral, and again, we're taking it around y here. So if we're rotating this thing around y, let me snip this thing and draw where this rotation is. Basically, it rotates like this. Okay, so this right here is the x, which is equal to potentially an f of y if we want it to be. But in our case, since we are going to be integrating it from 0 to 10 anyway along the x-axis, this integral from 0 to 10, we actually would prefer it in terms of x because we're integrating with respect to x, unless we want to convert it into this, y's from 0 to that 1/3, 12 to the 3 halves thing. But probably not. So we'll start with x and see how it works out. So the circumference would be 2 pi times r, which in our case is x or f of y, but we prefer x because we're doing it in dx. So 2 pi x square root 1 plus our function's prime. But essentially, again, if we go back to this here, we want our ds, and we can choose between dy dx or dx dy depending on our situation. Now clearly we want this thing in terms of x's, so we do want to describe this in terms of x. So if we called this like y prime here, y prime, that would be 3 halves times 1/3, so 3 halves times 1/3 x to the 1/2. This is our derivative in terms of x. So cleaning this up, we get 3's canceling, and we have 1 over 2 x to the 1/2. And this is our y prime in terms of x, which is what we want. So we have 1/2 x to 1/2 squared. Okay, so now we're going to go ahead and clean this thing up. X to the 1/2 and squared will then cancel, and 1/2 squared is 1/4. So we'll write that. This is 0 to 10 of 2 pi x square root 1 plus x over 4. All right. So we have dx now. Okay, so we want to start potentially by cleaning this up a little bit. Whenever I have this square root here, I'm hoping maybe I can combine these or something, because this is not going to be like a 1 plus something squared, so I can't do inverse trig substitution there. So that's problematic. I'm also, so the next choice that I'm having is maybe if I combine these. So if I had this as 4 over 4, then I might be able to write this a little bit better. We have the integral. I'm going to pull the 2 pi out since I don't need it. 0 to 10 of x times the square root of 4 plus x over 4 dx. So that would be the integral from 0 to 10 of 2 pi times the, we have x over 2 square root 4 plus x dx. Okay, because the square root is top and bottom, square root of 4 is 2, comes out. So I'm going to pull that 2 out, or in this case 1/2 out, and so the 2's and 2's cancel. We get pi integral 0 to 10 of x times the square root of 4 plus x dx. Okay, so now what we want to do is integrate this thing. Now we can't use u sub, so I'm thinking maybe integration by parts. So if we integrate this thing, we have, if we call this like our u and this our dv here, so u is x and dv is the 4 plus x to the 1/2 dx, and normally I would avoid that for a square root, but because this is linear inside, it's not that hard to integrate. So du then would be dx, and v would be 4 plus x to the 3 halves over 3 halves over divided by 1 as well, but this is that is the derivative of the inside here, as long as it's a linear, but it's just 1, so it's no big deal. All right, so that means then that v is equal to 2/3 times 4 plus x to the 3 halves. All right, so as a reminder, we have the integral of like or I should say our integral is uv minus the integral v du. That's what we're integrating here with by parts. So we're going to plug this in. We have our u, which is x, our v, keep in mind we still have a pi out here, okay? But our u, which was x, our v, which is 2/3 times 4 plus x to the 3/2, minus the integral of v, this 2/3, 4 plus x to the 3/2 du, which is dx. Okay, so we're going to clean this up a little bit more. Again, we have to be really careful here because this pi is being done into everything as well. So I'm going to go ahead and distribute it so I don't mess something up later. We have I don't know why it's not writing. That's super weird. It's like a dead zone. All right, it's no longer a dead zone. Okay, fair enough. So we have, nope, it's a dead zone. All right, fine. I'm not sure what's going on, but we'll just scoot over a little bit. We have 2/3 pi x times 4 plus x to the 3/2 minus, I'm going to pull that 2/3 out, 2/3 pi times the integral of 4 plus x to the 3/2 dx. Okay, so I wonder if I can write over. I can write. There's just this one little dead zone. That's super weird. All right, whatever. So we have 2/3 pi x, 4 plus x to the 3/2 minus 2/3 pi times. Now the integral, again, same thing. We can just add it by 1, so that would be 4 plus x to the 5/2 divided by 5/2 and 1, but again. And so we're taking all of this from our 0 to 10. All right, so let's clean this up a little bit. We have our, nope, 2/3 pi x, 4 plus x to the 3/2. Now, divided by 5/2 is like saying 2/5 multiplying. So 2/5 times 2/3 is going to be 4/15. So minus 4/15 pi times our 4 plus x to the 5/2. And again, this is from 10 to 0. All right, so we're going to plug 10 into here. Now we have 2/3 pi times 10. 4 plus 10 is 14 to the 3/2 minus 4/15 pi times 14 to the 5/2 minus, now we're going to plug in 0 into each of these. That would be 0 here. We'd have minus 4/15 pi times 4 to the 5/2. Okay, now this might be really ugly looking, but to be honest, I don't know that we can really get it all that much nicer looking. We can clean it up a bit, and I'm sure there's a bit of work we could maybe put into making it nicer looking, but it's never going to look nice, so I'm not going to really bother with that. Let's just clean it up a little bit. This would be 20 pi over 3 times 14 to the 3/2 minus 4 pi over 15 times 14 to the 5/2 plus 4 pi over 15 times 4 to the 5/2. So this is about as nice as probably this is going to get. I mean, we could factor out some things, but I mean, it's never going to be good looking. Now let's double check that this value that we get here is the same as our integral that we expect. So let's start with the integral. The integral that we started with that looked okay, but ended up being a horribly ugly number, such is life, was 2 pi x square root 1 plus 1 over 2, I'm going to put a parentheses around this, x to the 1/2 squared dx. So it's this 509 approximately, 509.5. Now let's see if our number is similar, or the same I should say, because it should be the same if I did everything right. So 14, to the 3/2 minus 4 pi over 15, 14 to the 5/2 plus 4 pi over 15, 4 to the 5/2. And we get the same value, 509.5. So this is our answer, as ugly as that is. We did get our arc length. Our arc length is approximately 509.5. Ish. And like I said, this is hideous, but sometimes we get really ugly things from these integrals, so it's not anything to be too worried about. The only thing I would note is that if I start getting something really ugly, then I definitely check to make sure I haven't made a mistake on the integral. And so essentially what I want to do is, if I do see that I make a mistake somewhere, I just start backing up and seeing, okay, well, what about like this? Is this integral the same? Yes, it is. Okay, then what about like this? Is this going to end up being the same, or this, or this, or this along the way? And just find where I made a mistake. But in general, it doesn't have to be nice looking. All right. So that has been our area of the surface of revolution. Again, these things, essentially, we really just want to think about them in terms of, which integration is going to be easier in terms of x or y. We can choose either one, but we have to make sure that the bounds of integration and the dx or dy agree. And in that case, then we just choose x's or y's to describe the rest of the things. Our radius, does the radius need to be an x because it's a dx? Sure. Does it need to be a y because it's a dy? Sure. Whatever. All right. So, thanks for watching.